So let's take a look at this example where we're going to use Pearson's chi-square test, or the chi-square test for association, or the chi-square test for independence. What we do remember about this test is that we need two categorical variables. So two categorical variables, and they can each have more than just two categories. So here in our little example here, we're going to have 1, 2, 3 categories for this categorical variable and 2 for that categorical variable. So let's have a look. So researchers investigate a new drug for high blood pressure or hypertension. They randomly assign 150 subjects to receive either a placebo, so that's no medication whatsoever, a low dose or a high dose of this new drug. So there's our categorical variable. We can think about that as the exposure, and there are going to be 3 levels or 3 categories as far as this exposure is concerned. And then as the outcome, or then the response variable, that's going to be, we can think about that as our disease variable. But they're going to classify the subjects as either improved or not improved. So they had some measurement and some definition by which they would decide if someone is either improved or not improved. And that's with respect to their hypertension. And the results are summarized below. So we see this table of observed data, or a contingency table. So we have our one categorical variable, its categories along the rows, and the other categorical variable with its categories along the columns. And now really, for in the sake of generality, it doesn't matter which one goes where. We just need this matrix, in other words, numbers of rows and columns of frequencies. So these are observed frequencies in our contingency table. So if we look at this fact, of those that received placebo, 20 of them improved and 22 didn't improve. So we might as well just complete, let me take a pencil, and let's just complete these marginal totals here. So let's put total on this side, and let's put total on this side. And we can see 20 and 22, that's going to give us 42. So we also know that 42 of these 150 subjects received the placebo. Of those that received the low dose, 30 improved and 20 did not. That gives us a total of 50 of our subjects who received the low dose. And then those that received the high dose, 48 of them improved, 10 did not improve. And that leaves us with 58. And if we sum over all of these, we should get 150, and indeed we do. So it's 150. And if we sum over these just to see how many improved and how many did not improve, so we'll see this sums to 98, and this sums to 52. And again, so 98 improved, 52 did not. And 98 plus 52 is also going to give me 150. So we've got our marginal frequencies there. And if we want joint probabilities, remember it's just each of these divided by the sum total. So we can think of this as our observed subscript 1, 1, row 1, column 1. Observed 1, 2. We can think of this as observed 2, 1. Observed 2, 2. We can think of this as observed 3, 1. And observed subscript 3, 2, row 2, column 2. Row 3, column 2, row 2, column 2, row 1, column 2, etc. So we have that, and now they say determine if there's an association between the intervention and the response. So we've got two categorical variables. Is there association between them at the 5% level of significance? So we need to do a couple of things here. We realize that we do have two categorical variables. We are going to just assume that these are all independent, and that we can think about using the chi-square test. What we do need, though, we need the table of expected values under the null hypothesis. So let's create that. I'm going to say table of expected values. This is my table of observed values, or my contingency table. This is my table of expected values. So table of expected values under the null hypothesis. What does the null hypothesis mean? Well, it says that these two variables are independent of each other. They are not associated. It does not, your outcome as having improved or not improved is not dependent on which of these levels of the exposure variable. They are just not associated with each other. And so we have this generic sense of our product rule when it came to our product rule, or our multiplication rule when it came to probability. And that said, if we have two events A and B, and we have the probability that A and B happens, A and B, that's going to equal the probability of A times the probability of B. Just two events A and B. And here we can think of these people, the subjects here, for them that would be the probability of being in the placebo group and improving. Placebo group and improving. And if these two were independent of each other, A and B, then we can multiply, just get the product of these two individual probabilities. And we know where this would come from and that would come from. These are just the marginals. And those are just the marginals. And if you think, how do we calculate the probability of A and B? So how would we calculate the probability of placebo and improved? Well, that would be 20 divided by 150. That'll give us the probability. So let's do that here, just so you can see. So the probability of being in the placebo group, placebo and improving, so both of those were to happen. Well, I'm going to calculate that just by saying 20 divided by 150. Okay, so how would I get back from a probability back to just a frequency? Well, I have to multiply. If I multiplied this by 150, multiply by the sample size, I would get back to just the 20. And that's exactly what we would do. We would say, take this probability and multiply it by the sample size. So the probability of A and B, that's going to equal, well, what I do on the left-hand side, I better do on the right-hand side. That's going to be n times the probability of A and the probability of B. Now, we are assuming that these two things, A and B, are independent. Placebo and improve would be independent of each other. So we're assuming this to happen. If that happens, this means on the left-hand side, I have this expected. So if we're talking A as being placebo and B being improved, this would be E sub 1, 1. This expected value under the null hypothesis. And on the right-hand side, we're going to see that many, or two of the n's at least can cancel out, because this is going to be n. The probability of A, if the probability of A was in being in the placebo, that's going to be this group here. And remember, let me take my pencil. This would be n sub 1 plus. Okay, this here would be n sub plus 1. So if we look at the probability of being in this group, probability of being in the A group, and we said A is this placebo, that will be n sub 1 plus divided by n. That's the probability of A. If the probability of B, if this B was improved, that will be n sub plus 1 divided by n. And now I've got two n's that cancel out, and I'm left with how to calculate the expected value under the null hypothesis. I'm assuming that these things are independent of each other. And that will leave me with n sub 1 plus times n sub plus 1. And that's all going to be divided, let me grab my ruler. That's all going to be divided by n. And remember, that's how we got to this fact that for every expected value, I look at that row and column. So n sub 1 plus, it is the row total. And I mean by that the total, because this is the 20 plus the 22. So the row total multiplied by the column total, that's this one, 98, divided by the number of people in my subject, in my sample. So it's always going to be row total times column total divided by sum total. It's as easy as that. So let's do that for these. Now you're going to need a calculator to do this, because for this E sub 1, 1, let's write them here. I want E sub 1, 1, the expected. Row 1, column 1, I want expected. Row 1, column 2, I want expected. Row 2, column 1, I want expected. Row 2, column 2, I want expected. Row 3, column 1, and I want expected. Row 3, column 2. Those are the ones I want. So for the 20, under the null hypothesis, I would expect 42 times 98 divided by 150. Now you're going to use your calculator. I've got this here as 27.44. Now I move to E12, so that's row 1, column 2. So that row total times that column total. So that's the row total, that'll be 42, that's the 22, it's row total, its column total is 52, so 42 times 52 divided by 150, and that gives me 14.56. 14.56. If I move to the city, what would I expect? Well, its row total is 50 times its column total is 98 divided by 150. That leaves me with 32.6, and that 6 just repeats. Put a little vinculum on top of that 666. You can round that off with a couple of sixes and then 7. And then for the 20, it's 50 times 52 divided by 150. I get 17.333, so 17 and a third. And for this 48, it's row total 58 times the column total 98 divided by 150. The sample size, I get 37.89, and then the 3 just repeats. And then for this 10, it's 58 times 52 divided by 150. That is 20.10106, and that 6 just repeats. So I have my observed values, I have my expected values. Now we've looked at the assumptions. This is two categorical variables. We're assuming that they're independent of each other. And when we look at this expected table, we can see that the values are all at least 5. So we've actually now got a lot of information here. We've done step number 0 because we've just calculated all these values that we would need, just summarizing all of this. And we've actually looked at, we're going to use step 4, we're going to use the chi-square test, and we've looked at the assumptions. So we've done quite a bit. So we've actually done step 0. Remember, step 0 is just going to be a summary. I'm going to summarize all of that, and I've got all of that here. So let's go to step number 1. And what are we looking at here when these two things are independent of each other? And what we're looking at is the population proportions, if these things, for these two, or these combinations at least of these two, if these two variables. So in the population, and all we have though is data on 150 subjects. So step number 2 is we're going to state our null and alternative hypothesis, and our null hypothesis is just going to be these variables are not associated. And our alternative hypothesis, we're going to say the variables are associated. Again, what that means would be that your outcome, whether you're going to improve or not improve, is going to be dependent on whether you got the placebo, the low dose, or the high dose. Step number 3, well, that's just going to be our alpha value, our level of significance, and we were told to use 5%. And step number 4, what test are we going to use? Well, we're going to use Pearson's chi-square test, and we've discussed already all the assumptions. We're going to assume that these observations are all independent of each other. It is two categorical variables that we have there, and here under the null hypothesis, we see that all of these values are at least 5. So Pearson's chi-square test. So for step number 5, what we need to do in step number 5 is, well, let's look at that test statistic. The test statistic is going to be x squared, and that is described by the chi-square distribution. We just need to know what the degrees of freedom are. So let me take my green pen here. I just want to just look at how do we calculate this degrees of freedom, nu. Well, that's going to be the number of rows minus 1 and the number of columns minus 1. If I can use that notation. And for us, this is going to be very easy. We had 3 rows. So we had 3 rows. So that's going to be 3 minus 1. And the number of columns is 2 minus 1. And by row and column, we mean how many categories are there in the exposure variable, how many categories are there in the outcome variable. And so 2 times 1 is 2. So this is going to be the chi-square distribution, and that is going to be on 2 degrees of freedom. And remember, that would be under the null hypothesis. If the null hypothesis was true, that these two variables are independent of each other, and I repeatedly sample from such a population, I'm going to get a bunch of x squared values, and theoretically they are going to be described by this chi-square distribution. So let's calculate x squared. Well, first of all, let's just put in green. Remember how to calculate this x squared. Remember, let's put it here, is that x squared, that is going to be the sum. So let's use one counter called I. That is going to go from 1 till the number of rows. And then I'm going to sum also over, let's make the counter j from 1 to the number of columns. And that's going to be observed ij minus expected ij. And I'm going to square that difference. I always get a positive, or at least a non-negative value. Of course, I can get 0 as well. Those two are exactly the same. And I want that as a proportion of this expected value. A proportion of that expected value. So I've got to do all of those. So let's just go here just to have a look. There's our observed, there's our expected. So we're going to say at the moment row 1, column 1. So observed minus expected squared divided by expected. Now we're going to move j to 2. That means the columns we move to column 2. So we jump this way. Observed minus expected squared divided by expected. So now we're done with the columns. Now I jumps to 2 and j jumps back to 1. So now we are in row 2, column 1. We have observed minus expected squared divided by expected. Move along, 20 minus 17 and a third squared divided by 17 and a third. Move along here, 48 minus 37.89333 squared divided by expected. And finally 10 minus 20 squared divided by 20. That's 0.10666. And that leaves me with the next squared value. So you've got to do all of that with your calculator. And you see that you should get around, let's say we're going to get around, double check on that on your own calculator. That's going to be about 14.227, thereabout. That's our x squared statistic. And now all we need to do is just to look at what the critical value is. So in step number 6, we're going to use decision rules. So let's look at our critical value for the chi-square distribution on 2 degrees of freedom, and we're using alpha equals 0.05. And if we look at that x squared critical value, and again, you've got to use your calculator for this, for 2 degrees of freedom, that's going to be about 5.99. So you've got to use your calculator for that. I'll show you at the end of this video. Let's have a look at that calculator. And of course, what we have here is that our x squared statistic is larger than our x squared critical value. And if it's larger than that, we know we reject the null hypothesis, and we accept the alternative hypothesis. So we're saying your outcome is definitely going to be dependent on which one of the levels of your exposure variable you get. Now you can go one step further and calculate a p-value. And for that, you would also need a calculator. And of course, our p-value is going to be smaller than, it's going to be one of those in that region of rejection. And if we look at the area under the curve from this x squared value, more extreme, it's definitely going to be less than 0.05. Let's take a look at the calculator. Well, before we do that, remember we have to add a step 7. Don't forget that. And you're going to write there is enough evidence. I'm not going to write it out, but you're going to say there is enough evidence at the 5% level of significance to show that the type of treatment for this hypertension and the outcome, whether people improve or not improve as far as the hypertension is concerned, are associated with each other. So let's have a look at the calculator online. So here we go. We are going to go down to inference. I'm going to click on OK. We're going to do a test, and what we want to do is come down to chi-square. I'm going to hit OK. This is not a goodness of fit test. This is a test for independence or test for association, because we've got 2 categorical variables. And now we can type in the values from our contingency table. So that's going to be 20. And then we had 22. Let's come down and across. Then we had 30. And we had 20. And let's come down. And then for the final, we had 48. And we had 10. Let's have a double check. 20, 30, and 48. It's very tiny on this recording. You can check on this Numworks website for yourself. 22, 20, and 10. Our level of significance is 0.5. Let's hit next. And there we get those expected values as we had them. 27.44, 14.56, 32.6667, 17.3333, 37.89, and then 20.106, etc. And we see those at least the 2 column totals. So let's go down to next. This is where we would see that all the values are at least 5. So we're good to go. And there we see our chi-square or our x squared statistic. That's 14.22269, just what we had. There's our p-value. It's right there for us. That's 0.00081. You see, times 10 to the power negative 4. So you've got to move this decimal point here 4 times to the left. That's going to give you 0.300008. That's definitely much smaller than 0.05. And by those 2 decision rules, either the critical value approach or the p-value approach, we're going to reject the null hypothesis. There's our degree of freedom. It's 2 as we had. Let's click OK, and we see this chi-square distribution under 2 degrees of freedom, and we see there 5.99, that was our region of rejection, and our x-squared value was way out at 14.2. So definitely tiny little area under the curve from 14.2 towards positive infinity, and it's definitely well beyond this critical value. Okay, now that we've done that, let's just look at this calculator, how to calculate the critical value. So I'm going to come down, I'm going to go to distributions this time, hit OK. I'm going to come down to chi-square, I'm going to hit OK. I'm going to put in 2 because our problem had 2 degrees of freedom. Let's just click on next. I'm going to click OK. And now I've got to look at this little symbol here on the left hand side. Way too small on this recording to see, but have a look on your own screen. It says if you look at this little colored area under the curve, it's calculating obviously always from the left hand side. And what I want to do is I want to have the 95% most common values. So I want to calculate a value here, a critical value, such that if I go from the left hand side from 0 here and I look at this whole interval going across towards positive infinity, what area here would be 95% of the area under the curve? So I'm going to leave that 0 alone, and I'm going to move across, and I'm going to say 0.95. So if we look at that, unfortunately it always just leaves an x there, but let's just say that that's the statistic. What's the probability that our statistic, for what critical value would I get to 95% of this total area under the curve? Let me hit OK, and there you look at it, it's 5.99. That's our critical value. And if you look at this area that's shaded now, goes to 5.99, and it says the probability that x is less than 5.99, so all this area here of this density curve is 95%. That's my 95% most probable values on that region. If we go above 5.99, that's going to be then the rare 5% of values. That makes this 5.99 our critical value. So I just want to go back and show you can think about it another way. Let's go back to this little icon there, click OK, and let's look at that upper tail. So on that upper tail, I'm going to say, well, I want the top 5%. That's this zone up here, this region up here. I want the least, the interval that has the 5% least probable value. So now if I put in 0.05 towards the right of my equal symbol and hit OK, we see also 5.99. That says this tiny little area here, that's the least probable 5% of x squared values that I would get if I were to repeat this an infinite number of times. I study an infinite number of times.